BIMSA Colloquium this time. This time, Professor Kupiainen will give us the talk, and Professor Zhengwei Liu will be the chairman.
It's my great pleasure to introduce Professor Antti Kupiainen, our speaker today. He completed his undergraduate education in 1976 in Technical University of Helsinki and received his PhD in 1979 from Princeton University and Thomas Spencer and Barry Simon. He became a professor of mathematics in 1989 in Rutgers University and in 1991 at the University of Helsinki. He was twice as an invited speaker at ICM in 1990 and 2010. From 2012 to 2014, he was the president of the International Association of Mathematical Physics. From 1997 to 2010, he was on the editorial board of Communication in Mathematical Physics. And in 2022, he received the Daniel Kahneman Prize for Mathematical Physics. And last year, he received the Henry Poincare Prize from International Association of Mathematical Physics. And it's great to have the leading expert in this topic to give the colloquium talk. And today he will present conformal field theory and patch integrals. Let's welcome the speaker.
Thank you for the introduction. So, topic is conformal field theory and path integrals. It's most of what I'm saying is joint work with these two people. So what's conformal field theory about? I mean, it's about field theory. It's about statistical mechanics on one hand, namely the theory of phase transitions, and second on phase transitions, which exhibit the conformal symmetry in large scales of when you look at phenomena in very large length scales. And there you see that the large-scale behavior is independent of relatively independent of the details of the small scales of the theory. And this is called universality. And the classes of universality, the classes of similar behavior, are described by these objects called conformal field theories. Moreover, it enters fundamental physics because all quantum field theories in short scales become conformally invariant. It's also a building block of string theory. And they have special symmetries which actually allow for very precise calculations and conjectures. And they have had a huge influence, especially two-dimensional conformal field theory in mathematics. So in representation theory, but also in geometry. So it's sort of, I think it was Alexander Polyakov who was saying that we have been describing and inventing a quantum theory of complex analysis. But despite all of this, a rigorous constructive foundation of CFT is lacking. And in this talk, I will talk about the probabilistic approach to two-dimensional conformal field theory. Okay, so but let's first look a little bit what this thing is about. So a probabilistic CFT is probabilistic. So we have fields defined on the space-time manifold. Let's just think of in the beginning just the space is the d-dimensional space. These fields are functions on the space, and there are some indices which describe which particular field you have. So I will call them V alpha. And since it's probabilistic, it means they are random fields. And in this business, you are interested in looking at so-called correlation functions, which means that you take a bunch of them at different points and take the statistical average over the number you get from that. So these correlation functions are the basic objects, and and these guys are the ones which show this invariance under scaling. So if you look at things at scale lambda x, so multiply every number by lambda, it's invariant modulo a power law, depending, and the power of lambda depends on which particular field you have there. So the coefficient there is called the conformal weight of the field. Okay, so that's scale invariance. It's not conformal invariance. It's actually sort of understood slowly that scale invariant theories, like in critical phenomena, should actually have conformal invariance, which means that the conformal group is an extension of what I just said before. And we are going to discuss only 2 dimensions in this talk, so let me jump now to 2 dimensions. And there the story is very familiar. Conformal maps are just the fractional linear transformations, Möbius maps of the complex plane. And the formula we had here, the only thing which changes is that the lambda is now can be spatially dependent. It's just the derivative of the map at a particular point. Okay. And since we are talking about Möbius maps, then the natural setup is actually not the plane, but the Riemann sphere. And actually, more generally, the natural setup is a Riemann surface. Now, if we are on the sphere, you can use conformal map to fix 3 points. We have 3 complex parameters at our disposal in the Möbius map, so we can map them to our preferred points, and then use this law with the psi prime there. To get that the 3-point function is completely determined, the spatial dependence is completely determined by this symmetry. And the only thing which is undetermined is a constant, which depends on which conformal field theory is and also which fields you have there. Okay? The powers here are just the conformal weights. And this number, which is undetermined, is called the structure constant of the conformal field theory, and that's one of the things which basic quantities which one would like to find in a particular conformal field theory. Now, that's not all. Okay, so that was sort of global conformal invariance, but there is much more what one expects in conformal field theory, actually in every dimension, but especially also in 2 dimension. Namely, one expects that you can sort of reduce all these correlation functions, which I wrote to you, to the 3-point functions. And the recursion is called operator product expansion. It says that within the correlation functions, if I look at, say, the first 2 ones, I can replace them by a sum of just one guy. So this is at x1 and at x2, just one guy at x2, and then a sum over various fields which we have there, and the 3-point structure constants, and then a differential operator acting on the rest. Okay. Well, if that literally holds, then I can keep on doing, right? Next I fuse these together, etc. So in the end of the day, I'm left with a 3-point function and lots of differential operators acting on it. But the 3-point function was explicit. So in the end of the day, you have a completely explicit expression as a sum, actually an infinite sum, of product of structure constants and some things which are completely determined by the conformal symmetry.
No dependence on x1 of the right-hand side.
I'm sorry?
There's no dependence on x1 on the right-hand side.
Yeah, so this is very bad notation. This differential operator acts on x2, but it depends on x1 and alpha 1 and alpha 2. Yeah. Okay, you can do it in various orders, this thing, and that gives you some consistency conditions of this operator product expansion, and that allows one to actually guess possible solutions. So what is a solution? Solution is what are the structure constants and what kind of fields occur in this sum here. That's a solution, okay? And this was applied by Belyavin, Polyakov, and Samolochikov with great success in the so-called minimal conformal field theories, one of which is just the two-dimensional Ising model. Okay, and more recently, numerically, this same idea has been used to get constraints on what the C's could be by Ritschkoff and many others. So how do you justify such a thing? Well, to justify it, of course, you would need to have some sort of formulation of conformal field theory independent of writing down such formulae. And what I will describe you is an approach to try to define it from a probabilistically constructed path integral. So what are path integrals? Well, that's of course the basic business of physics, statistical physics and high energy physics. So these correlation functions now are statistical averages over some ensemble of fields. So now we have a field I will call phi. That's the basic variable. It's like a coordinate, okay? So it's a function from your surface. From now on, we are in 2 dimensions, so this is a 2-dimensional surface. And it takes values in some manifold, usually called the target space. And then in that approach, you have some action functional, local action functional, defined on these fields. And these correlation functions are averages where you integrate over all configurations of the fields and weight each configuration by exponential of the action functional. Okay, that's Feynman's original path integral in the Euclidean setup. And the story is to set up such, try to define such path integrals and to see what you can do. Suppose you have set it up, okay? Suppose this makes sense. If the action function is local, it means that it's an integral of a density on the surface. That means in particular that if you split the surface into two parts, so let's say it's a union of sigma 1 and sigma 2, which intersect on a curve, on a circle, for instance, then the action functional should be additive, okay? So here's a picture. So you have fields everywhere, correlation functions at points on the surface. You have a curve which splits the surface into 2. Then you could try to do the path integral sort of completely formally, first integrating over all the fields on this side with keeping boundary conditions fixed. Then on this side, keeping boundary conditions fixed with the same number, and then after that, integrating over the boundary conditions. So once you keep each of these things here, which you do when you keep the boundary conditions fixed, you get some function of the fields on the boundary. This thing is usually called in this business amplitude. So it's a functional of the fields on the boundary, on the circle, okay? And then formally, then in this case, the 4-point function, in this case on a sphere, but you could do this on any Riemann surface, is reduced to computing such an amplitude and then integrating their product. So it's taking a scalar product. Again, there's nothing conformal here. This should hold. In some sense, one expects this to hold in any local quantum field theory. You can split your manifold and then do integrals like that. But the conformal field theory, this bootstrap principle, one way to formulate is then that these amplitudes, so in the example what I wrote here, this simple example, there are 2 points here and a boundary. So it's a function of the boundary. Now the claim is that these amplitudes are completely determined by the structure constants and the conformal symmetry. The sum runs over irreducible representations of the Virasoro algebra, and these functionals here are completely determined by representation theory. And this idea now generalizes to all correlation functions on any surface. This idea has long history. I think I don't know who first formulated, but it was Grain Segal who sort of wrote an axiomatic approach to quantum field theory doing that. And what I'm describing here is now actually a setup where you can prove Segal's axioms. Okay. So how to? But first you have to set up that. So let's start first. What action functional should you use? Okay. So my setup is the following. So let's have a two-dimensional Riemann, as I said, the Riemann surface. But let's think about it as a Riemannian manifold. So two-dimensional surface with a Riemannian metric, I call it H. And then the field is a map from that to another manifold, and that will be also a Riemannian manifold. Okay. And then I have this local action functional. And conformal invariance in this language, this is very natural in quantum field theory to have such a setup for your physical theories. So in that setup, conformal invariance means that it's a diffeomorphism invariance. So you pull back your metric and compose with the field, and nothing should happen. But more importantly, you can do the scaling. So you can multiply your metric by arbitrary arbitrary function, smooth positive function, and the action should be invariant. Of course, everybody knows a very simple example of such an action functional. That's just the Dirichlet energy. So this is called the free field. So it's a map from the surface to real numbers. And you take the derivative of the differential and take its length in this metric induces a metric on the one forms, and you take its square and integrate over the Riemannian volume. I call it VH. H is the Riemannian metric. And since you're on a two-dimensional surface, you can go to complex coordinates, and in complex coordinates, this becomes just a familiar looking expression. So this is obviously invariant under Weyl transformations because the conformal factor doesn't depend. So the action depends only on the complex structure, not on the metric only through the complex structure. Okay, that's the simplest. The next one is in physics called the nonlinear sigma model. That's slightly more complicated. Well, actually, quite a lot more complicated. So now the target space is a Riemannian manifold. I go immediately to complex coordinates because this will be again diffeomorphism and invariant guy. So I go to complex coordinates, and it's like the free field. Free field was just this and no indices alpha. But now let's have local coordinates on the target space. So I will call them phi alpha. Then the action looks like the following. You have derivative of phi alpha, phi beta, and then there are some functions of phi, nonlinear functions here in general, namely the coefficients of the metric in on the target space. Okay, so this is called nonlinear sigma model. There's a long history why the name is that. Let's not worry about that. But it's a familiar story in some part of mathematics also, because you could call this some sort of generalization of the Dirichlet energy. And for instance, it's extremar harmonic maps between the two manifolds. So it's a geometrically natural object. Okay, so those are sort of three quite obviously conformally invariant. But there is one thing which is not at first sight obviously conformally invariant. That's the Liouville theory. Again, you take the free field, but you add to it. The important part here is the exponential interaction. There are some parameters. Let's go to that in a second. But exponential of the field phi. That combination doesn't look conformally invariant because if I do y scaling of the metric, the volume, of course, pick a factor, so it's clearly not conformally invariant. However, if you add a linear term here is the scalar curvature of the surface and another parameter, and if you choose that parameter accordingly, depending on this parameter b here, the well, you can call it you want to call it a screening charge? Or? Yeah, you can call it, but well, yeah, but this is at the moment it's a real parameter here. Okay, and okay, why it's called 2b? That's historical. Okay, well, the important thing is here that this q is related to b, and this is really very historical, this action, because the extrema of this action are give rise to metrics on the surface with constant negative curvature. So this was studied by, it's called Liouville, but it was studied by Picard and Poincaré for uniformization. So that's the original root for this, but it's conformally, almost conformally invariant. It's conformally covariant when you do this wild rescaling of your metric. Then, well, you are shifting the field by this function sigma here. That's okay. I mean, that's how life is. And then there's a constant which doesn't depend on your integration parameter, the phi, which is called the conformal anomaly or Weil anomaly. It's something universal which occurs in every conformal field theory. And so this makes this theory actually a candidate of a conformal field theory. So I have introduced now the objects I want to describe, but they were classical. They were classical actions. We are supposed to make sense. Now take one of these actions and make sense of this path integral. Well, as written here, it doesn't mean anything really. So you should, what is the space of fields you're integrating over, etc. And the question is actually quite severe. In order to define it, you need to do something which is called renormalization. And once you succeed doing that and making sense out of it, it's expected that typically the conformal invariance is not anymore there. Okay, a very famous simplistic example is the so-called Heisenberg model. So here the manifold is just the sphere, and n-dimensional sphere with the usual round metric. And it turns out that to define this, nobody has defined it, but I mean we know what to expect, and you should replace. There's a renormalization which is just that you multiply the action by a number. I call it beta epsilon, where epsilon is your regularization. So you modify your field. You make convolve it, for instance, with a approximate delta function, scale epsilon, and you have to multiply it by a number which goes to infinity, or its inverse goes to zero. This is beta. It resembles temperature, and that's what it is. And this phenomenon is called asymptotic freedom. And in the limit, you don't expect the result to be any more conformally invariant. The action is conformally invariant, but the path integral, the conformal invariance is completely broken. And this is actually expected to be a massive theory. And actually, this is expected to be the case for all these target spaces if they are compact symmetric spaces. There are only some very exceptional cases of supersymmetry, Ricci flat cases, which are possible candidates for CFTs in this sigma model setup. Okay, looks like we are stopped there. So what do I want to describe now in the rest of the talk? Two examples. First is the Liouville theory, which I already wrote here. And this is, of course, an example which enters many places, but in particular, it's a basic building block of two-dimensional quantum gravity and random surfaces. Then I will also describe one particular sigma model whose target is the three-dimensional hyperbolic space. It will be not the sigma model, it will be changed. It will be conformally invariant because a term will be added to it. It's called the Wess-Zumino-Witten term. And again, it's a model which has been studied a lot because it's an example of the so-called ADS CFT correspondence. And then in the end, I want to actually, this look very different, these theories, but then I will show you how to actually find a map between the two. So the correlation functions of this can be written in terms of correlation functions of that, and vice versa. Correlation functions of this can be written in terms of correlation functions of that. And it has a very surprising connection to a completely different story in mathematics, namely so-called analytic Langlands correspondence. Okay, so what I will describe is that these two both can be probabilistically constructed using one tool from probability, the so-called Gaussian multiplicative chaos. Okay. So let's now look at that thing first. Let's first think about the free field. The natural probabilistic and geometric way to think about it is the following. So the free field was this Dirichlet action, but probabilistically, since a Gaussian exponential of a quadratic thing, then it should be a Gaussian measure. So the free field should be somehow statistically a Gaussian function. So let's take a Riemann surface with metric h like before. The free field is the following function. You sum over, you take the Laplace-Beltrami operator on your surface. We have a compact surface, so it has discrete spectrum on eigenvalues. One of them is 0, and the rest are positive numbers. Take the positive ones, take orthonormal eigenfunctions, and make an eigenfunction expansion and normalize them. There's normalization by square root of the eigenvalue. That's just for convention. And then you take these coefficients random, independent. Every guy has an independent, identically distributed normal random variable. So unit Gaussian. Take such a random sum. Okay, that's called the Gaussian free field. It's a random. It's actually not a function. It's a random distribution. It lives in Sobolev space with a negative index, but it's a relatively tame object anyway. So it's a random field. So this is the free field. In the Liouville model, you remember what we wanted to consider its exponential. Well, since it's a distribution, exponential as such is not defined, right? Nonlinear functions or distributions, you need to do something with them in order to define them. You need to renormalize them, that's a renormalization. And here it's rather simple, the renormalization. You modify it to some scale epsilon. And then the only thing you need to do is multiply it by a particular power, the epsilon, which depends on this b here. And then you take the limit. And actually, this limit exists. That's a classic result from the 70s. The limit exists. It converges. This is a random object. It's a random measure. It converges in probability to some random measure, and it's a convergence of measures, so weak convergence of measures. And the limit will be actually a rather exotic measure. It's not at all absolutely continuous with respect to Lebesgue, even if I write it in notation like that. It's called, this measure is called Gaussian multiplicative chaos. Again, funny name, it has an explanation, but let's not go to that. Important thing is that it's a completely well-defined random measure, and it's actually zero if the B is too big, but it's non-zero if B is less than 1, okay, in the kind of normalization what I write here. Okay, so now we have all the ingredients to write down the probabilistic Liouville theory. So this was our action. So we define the path integral by just saying that phi is the Gaussian free field plus the zero mode. I told you that the Laplacian has a zero mode. That's not probabilistic. That's just the real parameter. But in the path integral, you're supposed to integrate over all fields, not just the eigenfunctions different from zero. And the path integral is then defined by the following. Just plug in, you have some observable, which depends on the fields. Plug in this thing in here, plug it in here, and take expected value in the free field. That's this part here is in the E, expected value, and then integrate over the C. That's your Liouville theory. Okay. You also, in conformal field theory, this is an unnormalized expectation, so you also need to multiply it by certain regularized determinant, but let's not pay too much attention to that. Okay, you can write that definition now. Okay, and then that's what you know about it. Actually, you can do everything. You can now do the whole business of bootstrap with this. First of all, the primary fields are just exponentials. In the same way as we already renormalized the Gaussian multiplicative chaos, the primary fields, the fields which we are interested in are exponentials, and they are renormalized in the same way. The correlation functions, well, this is what we did some years ago. The correlation functions actually of these guys exist, and they are conformally covariant. The structure constants are then given by some probabilistic expressions, but you can actually then prove that they are given by a formula which was earlier found by these people, Dornan, Otto, Zamolodchikov, and Zamolodchikov in the 90s. And then the whole bootstrap hypothesis, namely that you do operator product expansions and compute these correlation functions, can be explicitly done on any Riemann surface with any number of insertions, and indeed all of these guys are given in terms of the structure constants and things which are called the Virasoro conformal blocks, so representation theoretical objects. Okay, I will not say anything about that because I would have to give a full lecture about that, except that here everything works in the Liouville model. So that's not a model which we would like to do. Okay. So let's now go to the Wess-Zumino-Witten model. Okay. So now we jump into these sigma models, and I take a particular one where I take the target space compactly grouped, for instance, SUN. And let me also call script G the Lie algebra. So there is, of course, natural left and right invariant metric on the group given which is just gotten from the Lie algebra, and on the Lie algebra of this matrix group, it's a killing form, but here it's just a trace of the trace of the product product of the matrices. Then the sigma model, what I wrote to you before, in this particular case, and with this metric is explicitly given by such an action functional. So you take z derivative of g multiplied by g inverse and z bar derivative, take the trace, integrate over the surface, normalize a little bit. And that's the action of the sigma model, specialized to this particular case. And just like in the case of the Heisenberg model, we don't expect, this is conformally invariant, we don't expect the path integral to be conformally invariant. We expect it to behave exactly like in the Heisenberg model. But it was observed a long time ago by Ed Witten that actually this can be modified. You can add a term to it, so-called topological term, so that once that term is added to it, topological means the term which doesn't depend on the metric at all. It only depends on the smooth structure on the surface. So that the path integral actually is defined, well, if defined, should give rise to CFT. And the topological term is topological also in the sense that it forces quantization of this number k here. So there has to be a integer multiple of this action functional. I won't write you the topological term because I will specialize in a slightly different model in a second, but many of you probably have seen that term. Let me just say that this has been one of the most successful conformal field theories in physics. So first of all, it's not only that it has this conformal invariance, but it has more symmetry. It has so-called Kac-Moody symmetry, which extends the conformal symmetry. So things like loop groups and their representations enter here. And it's also a very versatile conformal field theory, namely most of the sort of interesting rational conformal field theories, for instance, the two-dimensional easy model, there are algebraic constructions of them starting from the Wess-Zumino-Witten model. So it's sort of kind of universal, so-called compact conformal field theory. Okay. But the rigorous construction of the path integral is still open. That hasn't been done, and I'm not going to do that either here. I'm actually going to go through the back door and go back to some time ago. There is a conjecture, I could call it a duality conjecture, namely that these Wess-Zumino-Witten model correlation functions can be recovered from those of another Wess-Zumino-Witten model, where you replace the G-valued field by a field which takes, so like SU2, unitary matrix valued field by a field by positive matrix valued field. Okay, so you take the complexification of the group and you take the positive element. So instead of putting into the action function a unitary matrix, you put a positive matrix. So you take the Wess-Zumino-Witten action, which I didn't write to you, but you take it, and you plug in a positive matrix. Every positive elements of the complexified group are just G times G adjoint. Okay, and this is naturally the space of such positive matrices. Of course, this is invariant under multiplying by a unitary matrix. So this guy really lives on the homogeneous space of G's complexified group divided by the group. Okay, so it's a sigma model like we had before on the homogeneous space GC divided by G. And this is a guy which actually admits a probabilistic formulation, and actually surprisingly in terms of the multiplicative chaos. Okay, so that's what I want to describe next. And I will consider only the case of SU2. The other groups also can be given a probabilistic description, but let's just stick to this. So what do we have? Okay, for SU2, complexified group is the SL2C. And now if you divide by SU2, you get a three-dimensional space. It will be a contractible space. And it's actually the three-dimensional hyperbolic space. One way to see that is you write the positive matrix as upper triangular times its adjoint and parameterized. So you can parameterize everything by upper triangular matrices and take upper triangular matrix with the following parameterization. Of course, it has to have number and its inverse here because the determinant is 1, and then there's some complex number here. And let's use these coordinates. So exponential of phi over 2 here, and then complex coordinate gamma here. If you do that, then this space has the natural metric in the sigma model. The metric which we wrote down is just the hyperbolic metric which makes it a hyperbolic free space. Okay. So if I didn't put a topological term, it would be one of our sigma models. But with the topological term, this is a contractible space, so the topological term actually becomes very explicit, and the full action looks like the following. Very simple, right? So there is something which looked like the Gaussian free field before. There's another Gaussian-looking thing, but it's multiplied by exponential of that one. So they are coupled, and this is a highly non-Gaussian object, of course. And again, this is sort of has very interesting connections. First of all, there's been studied a lot as an Euclidean version of a CFT ADS3 anti-de Sitter space CFT. That's what you would write around. And what I want to describe is, first of all, how to construct this probabilistically, and then how it's mapped into Liouville theory. Okay, so you can forget everything what we did before, except remember the multiplicative chaos and the free field and this action functional. Okay. Okay. Now, very quickly, how do you define the path integral? It's obvious that, again, the phi should be the free field. So I put in phi the Gaussian free field, and it's 0 mode. Okay, that's great. Then this is a quadratic term in gamma, so you can write it integrate by path. It's a quadratic in gamma with a differential operator in between, which in this context it's called the Witten Laplacian in some context. So let's call it like that. But it's this simple differential operator here. Of course, the problem here is that it's a simple differential operator, but the field here is not simple. It's actually this random field, actually a distribution. So it's slightly exotic object. But it's obvious what the underlying structure here. So if I condition on phi, I have two probabilistic objects. So if I condition on phi, so I fix phi, then gamma is Gaussian with this covariance, which is the inverse of this operator. Okay, I write it here on the well. The inverse is there's a d bar operator here, so the inverse of d bar operator is some kernel, and the inverse of that, and in the inverse of that, and then there's a inverse of e to the 2 phi is e to the minus 2 phi is e to the 2 phi. So here's the formula for the covariance. So gamma is Gaussian with such a covariance, but of course this is a random covariance because phi is a random field, and actually a random distribution. But this looks like multiplicative chaos, right? It's an exponential of Gaussian field time the Lebesgue measure, and that's indeed the secret here. there is this business of normalization, so there is actually a determinant of this operator also entering the business. But maybe I will just tell you that this determinant is actually one of these determinants which you can evaluate. And it's given by, its dependence on phi is very explicit. It has a Gaussian piece, just like in the action. And then there's a linear piece like we had in Liouville. There's the Ricci curvature and the linear piece of phi. So in particular, the k here, the Wess-Zumino-Witten k is shifted by this guy to k minus 2. Yes, question? I'm sorry? This one. This is just the determinant without the phi. No, you put phi to 0. Yeah. Yeah. Of course, none of this really makes sense, what I'm writing here, because phi is a distribution and this formula is for smooth functions, etc. But we take this as our guideline here, and that tells us how we should give the probabilistic definition. I have to do a little thing because I don't want to have the k minus 2 here, but I want to have 1 there to compare. So you make this change of variables by phi going to b phi, where b is 1 over square root of k minus 2. Remember this number here. It will be the Liouville b, and it's related to the k like this. But once you do that, here is the definition of the path integral. In the H3 side, you do the following. You first take an average over gamma. So take the conditional expectation where x, the Gaussian free field, is fixed, over gamma, over everything what depends on gamma. So you have the observable, nothing else here actually depends on gamma. And after that, you take expectation over the phi, and then you integrate over the zero modes, both of the Witten Laplacian and the ordinary Laplacian. So phi is this guy, gamma is this guy, and conditionally on x, the gamma has this covariance. I'm writing it now on the sphere. This can be done at any surface, but the inverse of the d-bar operator on the sphere is just a Cauchy kernel. So that's what it looks like. In every surface, there is such a singularity. And you interpret this guy here as the GNC measure, the measure we described right before. Turns out that this makes sense, and the whole thing makes sense, actually. And it actually defines a conformal field theory with a certain central charge, which I didn't tell you about, but that's some characteristic of conformal field theory. And the primary fields are these exponentials. So there are exponentials in phi and exponentials in gamma. Why I have these strange numbers here? J refers to spin, to the representations of SL2C actually, and so does mu. So these are representation indices in the underlying symmetry here, but they're just these exponentials. Okay, so this is a conformal field theory. But what's interesting about this that it actually is now related to the Liouville theory. Okay. So here is the theorem. So if I take now these guys which we constructed probabilistically, they can be actually mapped to Liouville correlation functions by the following map. There's some trivial factor, but every point where there is a field here, there is a Liouville field which is slightly changed. So if I have alphas here, then I have some combinations of those alphas, and then the b it's multiplied by phi because I have this change of variables. That's trivial, but then there's addition of 1 over b, and then there are, depending on how many there are here, there are extra fields inserted in the Liouville side. These are so-called degenerate fields in the Liouville theory. And F here is a completely explicit function. I don't write it down. It's product of Green's functions and stuff like that. This similar formula actually holds on any surface, on any genus, and it also holds for twisted version of this model, where the underlying field, which takes values in this positive matrix, is actually twisted along the cycles of the. Actually, the way you do the twisting is parameterized by holomorphic vector bundles on the surface, and there's a similar formula for every surface. It looks a bit complicated. There will be extra integrals and stuff like that. Special examples of such formulae were conjectured by Ribault, Teschner, Hikida and Schomerus. Here we have a probabilistic proof and generalization of those formulae. It's also a very intriguing formula because it's really comparing two a priori completely different looking conformal field theories. One is the Liouville model, one is takes values in the reals, one is this matrix valued guy. But such formulae on the sort of classical level, not on this quantum level, on classical level, were studied in integrable systems over the decades by many people. I'm just putting random names here. And there is a rich set of integrable systems and connections to them in that field, and this is some sort of deformation of that story. Okay, this quantum deformation, and maybe I don't describe. Maybe we discuss this if somebody wants to hear about the twisting, but let's forget about that. But let me just continue with the discussion what actually this is connected to. So there are two interesting limits which one could take here. One is called the classical limit. So on the H3 side, classical limit means k going to infinity. And you remember there's this relation that B was 1 over square root of k minus 2. So k going to infinity means b goes to 0. So that's in the Liouville model. It's called the classical limit because somehow that you have to do some rescalings, but in the end of the day, you end up just the classical the problem discussed by Picard and Poincaré a long time ago. So the extremizer of the Liouville action is a metric on the surface with constant negative curvature. And the vertex operators, these fields, they are usually called vertex operators, they create conical singularities to the surface. Conical singularities in the metric on the surface. So there's a nice story about that. This classical and sort of fluctuations around that, studied by more recently by people like Kazhdan and others. That's a classical limit on the Liouville side, okay? But on the H3 side, the extremizer, so here the extremizer was a constant negative curvature metric on the surface. Here the extremizer is a completely different looking object. It's a Hermitian metric on a rank 2 holomorphic bundle, such a metric that the metric connection is actually flat. That's the extremizer of the H3 action. Okay? And if you plug in these vertex operators, they sort of create something which is called parabolic bundles. So parabolic structures of these singularities. So metric, but completely, entirely different fields of mathematics. Of course, this correspondence, what I wrote to you here, you take the limit here, it should be this holomorphic bundle story, and the limit here, it should be the uniformization story, and then this formula is deforming the story, but if you take the limit, then this should recover that story, okay? Then there is another limit which is sometimes called semi-classical, but usually called critical limit, where now here's the relation k going to 2, then k minus 2 goes to 0, right? So b goes to infinity. Okay, this is the limit where the correspondence is argued to relate to integrable systems, hitching systems, and operas in this story. This has been described by most forcefully by Teschner and advocated by Teschner and studied by Gaiotto and Teschner. And in particular, they are emphasizing that in that limit, you should be able to recover this sort of one of the simplest forms of the so-called analytic Langlands correspondence, which was studied during the past few years by these people. So the story, in a nutshell, is that this thing here, when you look at that limit, so here is a correspondence between correlation functions on this side and that side. On both sides, in this critical limit, there are some interesting sort of differential equations, let's say it like that. And there is an unexpected correspondence between those two, okay? There are two pictures here. One is called the geometric Langlands correspondence, where one actually doesn't look at these correlation functions, but one looks at the finer structure, which I flashed to you on the Liouville theory. These correlation functions are actually sort of pairings of holomorphic and anti-holomic functions, and those are called conformal blocks, and there should be some sort of correspondence between those. So that was the original story, and in this later version, it's a correspondence of correlation functions which gives rise to this guy here. Yeah. Well, we don't have a probabilistic construction of supersymmetric Liouville. There should be one, but it's a bit tough. Yep. Yeah, it's a bit tough. Yep. All right, so that's that story, and just what to do here? Well, Liouville, we could do everything. Okay, get all the conformal blocks, everything. Okay, in here it's more tricky. So we have construction of the theory, and we can relate it to Liouville, but that doesn't give us. We don't even at the moment know how to do Segal gluing. The gluing, which I wrote you in pictures of the path integral. In Liouville, you can define all these things and make it. Here, we don't know how to do that. And even once you do that, it still would be a challenge to do the bootstrap. So that's certainly an interesting thing to look at. I don't think the non-unitarity is necessarily a problem. We actually succeeded doing the imaginary Liouville theory, where the B is imaginary, and there that's certainly not reflection positive. So it's not a unitary theory, but okay, it remains to be seen. General group, I think probabilistic construction should go along the same lines, and what it maps to is a bit clear to me at the moment, but some Toda-like theory should be on the other side, so a correspondence. Then this is the hardest question, is the critical limit. Actually, Liouville theory has some sort of duality between B and 1 over B. And we have a complete solution of Liouville, so we should be able to expose this duality. Liouville is defined probabilistically only for b less than 1, but the duality should sort of give us this, and I think I've done my time now. So just let me thank you. Yeah.
Thank you very much. And any question?
Yeah, I'm just wondering if there are other examples of this Gaussian apart from SL2C over SU2.
Yeah, so for instance, SL3 divided by SU3.
Exactly.
Yeah. Actually, the structure here was that we had two Gaussian fields, right? But the other one was sort of depending very nonlinear on the other. There was this factor multiplying it. Every semi-simple Lie group will have a similar structure. So you have a bunch of fields. One is Gaussian, but depends conditionally on all the others. So integrate it out. Then the next one again turns out to be Gaussian, and depending on all the others, integrate it out. So that leads to similar probabilistic definition. But at the moment, it's not clear to me what that maps to.
But GMC formulation is defined.
GMC all the time, all the way.
Yeah. In that example, there were just two Liouville's on the other side.
I'm sorry?
So it was Gaussian on one side and two Liouville's on the other side, right? In your partition functions formula. Two vertex separators from Liouville.
Yeah.
So for the next dimension for the SL3.
Yeah, that's where I'm a bit stuck. Yeah. So first of all, what are you had to do some group theory, which I didn't, to figure out what are the correct vertex operators, and I don't think it's really very clearly discussed anywhere. And then I would like to have them in this exponential form, because or something like that, because then I can keep on doing my Gaussian integrals explicitly. I didn't explain to you how this correspondence comes, but it comes by just doing Gaussian integrals of exponential functions. Once you have defined the model, it's not difficult to do this. You have to be careful and you have to show that everything exists, etc. But in the end of the day, it's just doing Gaussian integrations. And some miracles are happening in the end, but technically, all the work is just to define the guys.
Can I ask you a naive question? Yes, I am in the parallel universe.
Yeah, that's what I was looking for, the gods.
Thanks for the great talk. So I have a very naive question. So about this quantum deformation of analytic Langlands correspondence. So I'm learning from your talk that the correspondence between these two CFTs, there's some kind of Q deformation of that Langlands correspondence.
Yep.
So on the Bungee side, as far as I remember, this an algebraic level, these quantum deformations on the Bungee sides are given by Baylinson and Drimfeld quantizations of Hitchin systems on the Bungee side. My question is, what do we get for the Q deformations on the other side, where we have the local systems on the curve? So what is the Q quantum deformation we get on the other side to make this correspondence work?
Right. I mean, the quantum deformation is really just what I wrote here, namely this correspondence between the correlation functions. Okay. So it sort of looks like I'm talking about replacing deep things by something simple. Of course, these correlation functions are not simple. Okay, you have to, but that's the correspondence. It's just correspondence between two sets of correlation functions. in this semi-classical limit, you end up with differential equations and correspondences between integrable systems and stuff like that. It's all hidden here. Okay. Formally, Teschner did some calculations where he checked what follows from such a correspondence, and he was recovering some things about Hitchin systems and operas and stuff like that. Yeah.
I see. But is it easy to extract or reverse engineer this very correspondence that you have written?
Yeah, that's
on the local system side. What algebraic objects I should be looking at? I mean,
well,
it should be Q deformation. It should be some kind of quantum deformations of holomorphic bundles with connections. But I want to know what kind of deformation.
Yeah, the short answer is that I don't know. I don't know. I mean, all I know is that this classical limit, namely the b going to 0, which is not really going to the Langlands, that is something very accessible from a probabilistically. It's just Lash deviation analysis, and that's very doable. Okay, but the critical case is more tricky because I don't really have definitions of either side in that realm where k goes to 2. I have some hopes that maybe using Liouville duality one can have a formula which then you could study the limit of, but that's more tricky. And the second answer is that I'm a bit of a beginner in the Langlands correspondence, to put it mildly.
Okay, thank you, and thanks for the great talk.
Thank you.
Sorry, maybe just a quick follow-up on the correlation functions. When you talk about this imaginary Liouville construction, sometimes you can make a double copy of this.
Yeah, that's very interesting.
Let me just finish what I want to say, because I would anticipate to see the relation to quantum volumes.
Yes, exactly, and those are things which are exactly. There will be quantum volumes. In this case, there is the volume conjecture, and this is something which, well, should be visible in such formulae, but it is also, the short answer is yes. That's exactly what one of the problems which should be accessible. Yeah.
Any other question? Let's thank the speaker for the beautiful talk.